fine. So generally, let me start with the introduction. This is just a relatively new work which is being performed by PhD student Rebecca, and I should acknowledge the co-authors. It is Dr. Raman Maiti and Professor Anish from Latvia University Group Mechanics of Advanced Materials. So let us now look at the idea behind the skin. So just if you have a medical background, so just you know significantly more than engineers do, so that's why clearly, sorry, but I will give you the idea that everything what we have here, for instance, the skin, it is a rather complex matter. As you can see that we can subdivide this into several layers, and each layer have also its own stratification, and they have a significant difference in the mechanical properties. And clearly, we would like also to consider how to deal with this. We are trying to bring a little bit of the structural integrity. We would like to deal with this as with any other mechanical structure. And clearly, these materials, they are anything but our traditional structural materials. So that's why we should consider them in a slightly different way. But still, the wood point, unmodestly, tomorrow I will do a plenary section, plenary lecture on the biomedical materials. So that's why it's a kind of introduction to this as well, that so in this community we are more accustomed, the total European Structural Integrity Society, to the structural materials. Here in room, there are probably people who know significantly more about the differences between the biotissues and structural materials. So generally, if we are looking at the mechanical behavior of skin, clearly we can see a curve which is pretty well known, and this is the type of the typical soft biological tissue that we can see. And clearly we have here deformation, but the interesting point is that we can have totally different type of the mechanisms which are underpinning these processes. Let us generally still consider what can be done. And you do know that this is the problem with the biological materials, that we have generally a problem that tests on the live specimens, so just us. So we do perform up to the pain level, clearly can be done. So, but mostly people are using the animal models to do this, and there is also some ethical constraints. Also, people are doing this on the dead specimens. But the dead specimens, especially the soft tissues, clearly the question of transferability of the properties of the data obtained on the dead specimens compared to the live ones. So this is a matter which is a serious one, which would not be covered in this presentation. So what we are doing as an engineers, we are trying to find a substitute which will allow us at least to have some idea what can be achieved under different loading regimes, and after this has been done, then clearly there is a possibility to better use of any other test, whether it is in vivo or in vitro. So this is the work in the progress, and these are the major stage of its methodology. We would like to introduce a substitute for skin, and silicon is an obvious case, and many people have done this. And then we would like to see how this affects the realization of the deformational process. That's why we are using the digital image correlation. And later on, we will be also doing models. And the idea behind the names which you can see here, these are hyperelastic models which historically were developed mostly for the polymeric materials. but the community of the biomaterials have taken them on board because this is type of the behavior which I have shown you before. So generally there are not that many special biomedical mechanical models apart of the famous one which was initiated in the work of the Ogden, Holzapfel, and Gasson, for the fibrous structures, which is now becoming very popular for the soft tissues, especially for the arteries. And so let us now just go to what has already been done. So generally the idea about the specimens is that we should try clearly to retain the close dimensions to what we have, and usually the skin thickness, and as I've already shown in this, there is some, as always, vagueness in the definition what skin is specifically one, but I can very quickly to give you that we are considering in terms of the skin, we are considering the entire complex layer. This provides you with the thickness of around between 1.3 to 3 millimeters, and so that's why we are preparing. We are preparing the typical specimens which are being cut with a punch, and we were using the different thicknesses in order to consider the effect of this in our work. Then there is an inevitable problem which if you have done this is the challenge of putting the speckled pattern on the surface. So as always, first of all, one reason for this is that the surface of the polymers is not always very suitable for this, and secondly, we need also to consider that the level of deformation is relatively high, so that's why in many cases when you are applying relatively large deformation, you are having the peeling off the speckled pattern, which we will definitely try to avoid, because then we will get the wrong information. So here is after, so as always in the research, I don't like the word easily. After many trials and weeks of the work of the PhD student, now it is easily can be done, but we should appreciate that everything is not easy in the life of the people who are doing especially experimental studies. So, and then we are using a combination of the testing machine with the digital image correlation. Here you can see the parameters what are important in the description of the specimens and the loading regimes, and we have tested 5 specimens for each size that I mentioned before. And now, come on, do what? Yeah. So now you see that this is the window, which is focused here, and this is what is happening clearly, because you have the kinematics of the movement of the specimen, so that's why it was going up. But you can see that we can have a reasonably good resolution of the deformation fields here. You see that this is it is not seriously non-uniform, but there is still some elements of the non-uniformity related to the differences in the local mechanical properties. Now it is lacking, so it is all. Okay, good. Yeah, and then now what is supposed to be done after we have got the data. We are going to simulate this material, and it is not skin yet, So that's why we are modeling the silicon rubber, and for silicon rubber we do have a rather good set of the data available in the literature. We can also suggest to use other tools which have all the suitable set of the models to be tested in this. So just once more, so just for those who are keen to get the ideas about the equation behind all these models, these are three major potentials, so just Aruda voice, third order Ogden and Yeo. So just they are presented in a traditional way. So just I'm not going just into details here. And generally, these are the parameters for the material. So just you can see here that the number of the parameters depend on the model together with the assumptions. And generally, this is a result of the comparison, and you can see generally just based on the literature data that even just some models that do not demonstrate at this level of deformation, as you can see, up to 50, that suggests same type of convexity concavity. So just be careful when you are using the different models. But at the end, we have found that the most reasonable model was the Aruda voice, and you can see here, so just this is the data obtained directly from the instrument and from the DIC. There is just some gap, which is nearly constant at large deformation, and we have just the Aruda model going pretty well along this line. And so generally, so just there is no need to speak a lot about just conclusions, but at the moment, as I've said, this is the early stages of the PhD project, but the important one that we have got a reasonable way to deal with this. And so generally, this is a preparation for the future work. When I've shown to you, I wouldn't go so just many slides back to the beginning, but you do remember that this is the stratification of the skin with the four major layers, and you see the significant difference in the thickness of this. Clearly, it all depends on the species and the position in this, and this is what would be the next step when we will get all the properties for all the layers, and so just to deal with this in the different type of applications. And thank you very much for your listening to this.
Yes, thank you. It's a very interesting project, really, and I was wondering, how will you tackle the problem of validating the properties of this silicon rubber, this surrogate of skin, to the properties of live skin, as you were saying earlier, without having to resort to the differences?
So just generally, we've tried to do this before, haven't we? Yes. So the idea of how it is being done, and this is just what I consider a very important part in the entire approach to the problems of dealing with the properties of the live biological tissues. You are supposed to use inverse or semi-inverse analysis. So just inverse, it means that it is well posed. We can do this, we all do know it because of the nonlinearity. And the very important part is its significant level of variability. But to give you an idea, for instance, what we have done, it was just with the Ministry of Defense in the United Kingdom. So we have volunteers in our group. So I wasn't among them, but we have here representative. So this generally, we have devised a special device, which is effectively nothing else as an indenter, but a macroscopic indenter, which also have the capability of measuring the thickness of the layer as well as the light load. And then we were we have, there was a project, we have 22 points on the lower limb position in different ones because we have different layers of the properties. So, sorry, I'm speaking not only about the skins explicitly. I'm speaking rather about the measuring of the properties of the entire soft tissues, including the muscles. But clearly for skin, it is also possible to be done. Then we load this just below the hair level, and then we obtain the caps of the displacement versus the applied load. And then we've got generally the situation which is very nice on the one hand, because any model will do, because the set is so broad that you can find a curve which suits your model if you want. The question is how to do this more reliable. So clearly, on a more serious note, it is, so when I'm speaking about the semi-inverse approach, we're running in parallel, so it's not really in real time because the simulations are long. We do the simulations and we are playing with some of parameters which can prescribe or can affect. For instance, the friction or frictionless condition. For instance, you put here the oil, you don't put here the oil, and so on and so on. And so eliminating the different factors. And then you are trying to match. So understanding that this is ill-posed problems, but this is because we start with the rather close approximation to the model. This is the one. Another part is clearly we are looking at the situation when we are testing the skin of the for instance of the animals, but it is of the dead ones. So that's why it's all coming together. But this is still the work in progress for the community, because at the moment I can give you even for the hard tissues like bones, there is still, if you go to the literature, the scatter even in the stiffness is by a factor of 3, though we've done quite a lot of studies and introduced all viscoplastic characteristics, because there is a huge amount of this. But sorry, it's a little bit long question, but this is what I only see. And this is how people are doing, there are different other methods people are using, for instance, the negative pressure, and then they look at the profile of the skin, when they are applying this through the feedback, and different paths, but this is the only way, from my understanding, to deal with the live tissues.
Thank you.
Okay, yes, sorry then. No, you were
okay. Thank you for the very interesting talk. I was wondering on the modeling part. First, why did you specifically chosen those models? And if you considered using, for instance, microsphere models or approaches that, for instance, for those models, the shear modulus of the network is relevant parameter, and there are approaches that consider the microstructure of the networks, phantom models, Gaussian approach, tree-like structures. If you ever consider doing this, and also relaxing, for instance, the affine deformation hypothesis to allow the chains to deform in a non-affine way.
Okay. So the answer should be a new lecture probably. But it's trying to give you the information international. So this is first of all the work for the future. So putting go in an order. So these models, because the tissues, they are hyperelastic. So that's why this is where we start, and because the hyperelasticity was started on polymers, we do consider that we can always find a polymer which is not very far away from your biotissue. So this is the second one. Then the question is clearly about large finite versus infinite means small deformation and so on. This is a good point, but we need also to understand the importance that clearly we are given here skin is part of a structure. It is not a material. And in many cases, its behavior is still due to the hook stresses. So from that point of view, generally the microstructure is important at the cellular level, but at the level of the macroscopic behavior. What we would like to look at the pattern of force, how this would affect the one. But I hope that the internal microstructure, a part of this less by stratification, so would be enough, at least at this stage of the research.
Yes, thank you. I just want to know the shape of the porcine skin, the pig skin, to repeat the test. How the shape is going to be? Is it
So the porcine skin, it is not that great from the point of view because it's significantly thicker than that in the humans. So still it is useful for if you are studying the porcine's skin in its own right. So from that point of view, we are still, and this is just it reminds us, if you're looking at the history of the mechanics of material, we are doing the first steps. We are looking at different features. We are moving to just thick skin will provide us a possibility to study the effect of the thickness. On the other hand, and I will be just already mentioned, the problem is that, for instance, the humidity and the effect of the environment is significantly a tougher factor than anything concerning the microstructure and what's not. So that's why the transferability between the live and dead tissues is a very important feature. I should stop myself here because I don't want to misuse my position as a chair of this session, because we still have other presenters, not only me here. So let me ask, do we have here Jan Dan Kumar or